Today we will discuss the analog multiplication. We can multiply the two voltages, using log and anti-log devices. Log and anti-log devices can be realized by using the op amplifiers. First we learn how the op amplifier acts as the logarithmic amplifier. We already know a transistor equation for the emitter current. Emitter current of the transistor depends upon the emitter voltage, by the equation IA equals to IS. IA equals to IS. IS is the reverse saturation current, E raised to power QVE upon KT minus 1. This is the voltage VE. Emitter current is a function of this voltage, and that function is exponential. And other parameters for a given temperature like T is constant, K is Boltzmann constant, and IS is reverse saturation current. This is the circuit diagram for logarithmic amplifier, and here this is a transistor. This is emitter terminal, base is grounded, and this is the collector one. Collector is attached to the inverting terminal, and emitter is attached to the output side. Base is grounded, and to the inverting terminal, input is applied here through a resistance R1. So because there is voltage in R1, the current will flow along this path. This current is, because this is a collector, so this current is called the collector current. So the collector current flows like this, and collector current and emitter current. Here will be the emitter current. They will be approximately equal, because the base is grounded. So this is the transistor equation for emitter current. IS is the emitter saturation current, and very small, 10 raised to power minus 13 ampere. E equals to IC because base current is, base is grounded. Then IE written as IC here. So IS taken to this side. Then now because this value will be greater than 1. You know why? Because denominator is very small, right? As Is is approximately equals to 10 raised to power minus 13 ampere. So this is very large. So 1 may be neglected as compared to this. So now taking natural log to both sides, not log, ln, natural log. So exponential and natural log cancels out. So this exponential, when we take the natural log to both sides, natural log and exponential, they cancels out, and we left this parameter. Okay, and natural logarithmic to this side. Okay, then we calculate the value of VE. Okay, VE equals to, now here this virtual ground, so IC becomes this voltage divided by this resistance. So this is IC, because this is ground, means zero potential. So substituting, the value of IC here, IC is this value. Substituting here, now this denominator, let we call it this is a voltage because resistance into current, and we call it reference voltage. So this is V. So here the output voltage will be V0. Output voltage will be V0 equals to this minus VE. Okay, and substituting the value of VE here. So this is the last expression, that the output voltage, output is proportional to logarithmic of the input voltage. So this is the expression of the log amplifier using op, right? Now we'll discuss how the op amplifier can be realized as anti-log amplifier. Okay, this is diode, and diode is connected to the inverting terminal, the output, and here the feedback resistor RF. V input is applied here, and current is flowing, diode current, forward current I, IF and I will be equal, and positive terminal is grounded. Here IF and I will be equal, because there is no current drawn by op itself. Op never draw any current, because this point is, this is at the virtual ground. Because this is ground, so this will be virtual ground, mean 0 volt. Now we are having, so this is the diode equation, forward current, okay, equals to this current, of a diode is a function of the input voltage, and current increases exponentially, and this is a voltage which is a function of temperature, and eta is again a constant depending upon it is silicon or the germanium, the material. Okay, but basically this equation shows that forward current is a function of the input voltage, and B is at the virtual ground. Okay, So op amplifier, input current drawn by op is 0 always under ideal condition. So IF equals to, IF and I, they are equal, and IF, equals to IA, and what is, I current. I current is voltage at here minus the voltage at here, mean the potential difference across RF, okay, divided by RF. Now because VB equals to, 0, VB equals to 0, so this becomes the current I equals to minus V naught over R. So substituting the value of I here, written here, okay, VB 0. Now just simplifying. Then output voltage is, output voltage is proportional to exponential. Output voltage is proportional to exponential. This is exponential. And the input voltage. Exponential means the anti-log. Okay, output voltage is anti-log of the input voltage. Now what's the analog multiplication? How can be realized by using the logarithmic amplifiers? Vx is the input voltage given to a logarithmic amplifier. Vy is again the second input again given to the logarithmic amplifier. Output of the two logarithmic amplifier given to the summing device. So here becomes the logarithmic of Vx and logarithmic of Vy, logarithmic of Vx plus logarithmic of Vy, log A plus log B is log AB, okay. So log AB means logarithmic of Vx into Vy, then given to some anti-log device, and ultimately the output becomes Vx Vy upon V reference. So output is, output is multiplied of the two input voltages. How we get a square of a given number? the two inputs XY are connected together and given a common voltage VI. VI is applied to X as well as VI is applied to Y. And this is a multiplier, So output resistance 10 kilo ohm. V0 is VI into VI upon V reference. So VI square upon V reference, this is what is required. Now the problem is how the multiplier can be used for the phase angle detection. First Vx is Vmx sine omega t. Vy is Vmy sine omega t plus theta. Now here the phase is omega t. Here the phase is omega t plus theta. The difference between the two, in phase, the difference in phase between the two voltages, it is this theta. So this is the result of the multiplier. This is the results of the multiplier. Substituting the value of Vx and Vy here. Now just simplifying, sine A into sine B. Applying the formula, trigonometric formula, and we'll get now the important is here, this term does not contain any omega. So if does not contain any omega, so this is the DC term, not AC. This part is AC, okay? This is AC because it contains the frequency. It doesn't contain any frequency. Theta is, some constant, some phase. This is the DC component, okay, independent of frequency. Now we will discuss the how we can realize the divider using multipliers. How we can realize the division using multiplier circuit, okay. So this is a multiplier actually, and this one is the op. They are the two inputs. They are having this multiplier x. X is one input, and output of the op is connected here. That becomes second input becomes V0 for this multiplier. For multiplier, two inputs V0 and X. Now here, they are the two inputs and the output. output is connected to the inverting terminal through resistor R. And to this inverting terminal, another input VZ is connected through again resistor R, right? And to this X, the at X terminal, the voltage is Vx. So two inputs, Vx and Vz, and we have to divide the two. Because this point is at the virtual ground, op amplifier never draw itself any current. Okay, so the current will take this path. So if you were calling some current here and we're calling some current here, then that two currents will be equal. Okay. Now here the voltage is Vz, here the voltage is 0, potential difference is Vz minus 0, and resistance is R. So Iz becomes Vz minus 0 upon R, that is Iz. Now Ia current, okay, along this resistor R, this at this point voltage is 0, at this point the voltage is Va, so difference is 0 minus Va divided by R, that becomes Ia, and Ia and Iz are equal. Now, for this multiplier, there are two voltages, Vx and V0. There are two voltages, Vx and V0. So, therefore, the output at here, Va, will be equal to, by the formula of multiplier, Vx into V0 divided by V reference, right? Substituting this value of Va here, then Ia becomes equals to this. Now Iz equals to Ia. So instead of writing Ia, we write Iz. Taken this R to this side, Iz into R becomes the voltage. And Iz into R, this voltage is what? Iz into R, it is Vz, right? So Vz equals to this. So output voltage V0 is some constant and Vz upon Vx. Vz and Vx are the input voltages. So output voltage is, is the division of Vz and Vx. So let we modify the divider circuit. The Vx and V0, now here they are connected together. They are not two different voltages now. There is a one which is V0. Mean V0 at this terminal, V0 at this terminal. Their circuit is the same. And here input voltage is Vz. Okay. The problem is finding the square root. We are using the same formula because here V0 and Vx, they are the same. So instead of writing here Vx, we write V0. Okay, V0 and V0. V0 taken to this side, that becomes V0 square. Let we take the magnitude of this minus Vz. We take the magnitude of minus Vz as the mod of Vz, and to V reference, V0 is the square root of this.